Right, so this video is going to do an example problem on finding a unit tangent vector and then a unit normal vector for a specific function. It's mainly to show you that this can get kind of messy. So, let's get started. Example. We'll find the unit tangent vector t of t and a specific unit normal vector n of 2 for r of t equals t comma t squared. So we're only going to work in 2D here. Now you might remember the normal vector points directly into the curve. The unit normal vector, the one that the n of t. So let's first do t of t. By the way, this graph right here is y equals x squared. So you know that this graph is going to look like this. And in this case, as t gets bigger, x gets bigger. So it's moving around the curve this way. So you can kind of picture that at t equals 2, we're going to have a unit tangent vector pointing off like that. The unit normal vector will have to point directly into the curve. So that'll be n at 2 and t at 2. Now we're gonna find t of t first. So t of t, remember, it's really just the derivative divided by its own length to make it a unit. So let's see, the derivative of r of t is 1 comma 2t. And the length of that is just the square root of 1 squared plus 2t squared. So we're going to get, I'll put that non-vector part in front. So it's a function, but it represents a scalar. And then I'll put the vector right here. So that's t of t. Okay. If we wanted to figure out what it was when t equaled 2, well, let's plug in 2 and see. So it's 1 over root 1 plus 4 times 4, 1 over root 17, and then 1 comma 4. So it's 1 over root 17 and 4 over root 17. So it's got to be pointing upwards like that. You can kind of see from that picture that's what we got. Okay, so let's take a look at n of t. Now we know that that is defined as t prime of t normalized. Now, if you wanted to do this, you could. This gets ugly fast because t prime would require you to take the derivative of this vector in that box, where you'd have to treat this as a regular function, this is a vector function, t. And then when you want to take the derivative of something like that, of f of t vector function u of t, you have to turn it into a product rule. And so it becomes f prime of t u of t plus regular f of t u prime of t. Now the u of t and u prime of t isn't too bad, but that f of t, taking the derivative of that, is going to be more annoying than you want it to be. And then you have to after you get all that, you then have to divide by its magnitude. So then you're going to be squaring this thing and taking the square root of it. Squaring the individual parts, because this is a vector, remember. Okay. So instead, we only need n of 2. So really all we need to do is find t prime of 2. We don't have to worry about all of t, all of the general derivative. So this is what we want. Okay, so we still have to, unfortunately, take the derivative of t. But then I don't have to simplify it at all. I can just plug in 2 as soon as we get it. So we're taking d dt of the 1 over root 1 plus 4t squared times 1, 2t So that's going to turn into the derivative of the first times the second. So derivative of the first is going to be, let's see, this is the same thing as 1 plus 4t to the half, or negative a half. So it's negative 1/2, 1 plus 4t squared to the negative 3/2, times the derivative of the inside, which is 8t, and then times the vector 1, 2t. So this is the f prime u, plus, and then keep the first one the same, so it's 1 over root 1 plus 4t squared times the derivative of the second one, so that'd be 0, 2. Okay, so that's pretty ugly, but we don't have to simplify it. All we have to do is plug in 2. You can imagine that trying to simplify this and then to figure out its length to get that would be pretty annoying. But when you can plug in 2, it simplifies pretty well. I mean, it's still kind of ugly, but at least it simplifies. So we've got negative 1/2, 1 plus 4 times 2 squared to the negative 3/2 times 8 times 2. And then the vector that we're multiplying by is 1, 2 times 2, plus, and then 1 over the square root 1 plus 4, 2 squared, 0, 2. And then if we simplify that a bit, let's see, the 1/2 here cancels with the 2 over there. And then this will turn into, let's see, a negative 8 on top over a square root cubed. I'll just write, let's see, that's 17 on the inside. So it's 17 to the 3/2 times the vector 1, 4 plus 1 over root 17 times the vector 0, 2. Let's see what happens with that now. So then this is going to turn into negative 8 over, now 17 to the 3/2 is really 17 root 17, and 1, 4, plus 1 over root 17, 0, 2. Let's see, what else can we do with that? We could multiply this by 17 over 17, so I get a common denominator. And then I'm going to factor out a 1 over 17 root 17 and be left with negative 8 times 1, 4 plus 17 times 0, 2. And then this whole thing turns into 1 over 17 root 17. Let's see, negative 8, oops, plus 0. And then comma, negative 32 plus 34 would be 2. So there we go. There's your t prime of 2. Now if I wanted to figure out its length, I can leave that constant out in front because it's really just this length, the length of that vector times this constant. So that's going to be 1 over 17 root 17 times the length of negative 8, 2. So negative 8 squared plus 2 squared. So let's see, that's 64 plus 4, so 68. So it's going to be root 68 divided by 17 root 17. And this, let's see, this turns into, you can take a 4 out of that and you have 17 left over, so it's 2 root 17 over 17 root 17. So that's convenient. And the length is 2 over 17. Okay, so let's go back to finding n of 2. And remember, that's going to be this divided by that. So on top, we've got 1, whoa, we've got 1 over 17 root 17, negative 8, 2, over 2 over 17. If I multiply the top and bottom by 17 over 17, those guys cancel and these guys cancel. And I could throw the 2 under there. So I get 1 over 2 root 17 times negative 8, 2. And then I might as well put the half inside here. So it becomes 1 over root 17, negative 4, comma 1. Or if you want it as a single vector, negative 4 root 17 over root 17, 1 over root 17. By the way, I found an applet that shows you how the normal vector appears. So I just searched for TNB, or I searched for unit tangent vector applet, and this is what popped up, something from GeoGebra. And I turned it into a 2-dimensional graph. You can kind of see, so I inputted the function t squared. I just made the z value 0, so it's really, over here it's a 3D picture. But in 2 dimensions, let's see, I need the x and y axis. Sorry, this is a little ugly. There we go. So we're looking at it essentially straight down above the z-axis here. And you can see the unit tangent vectors pointing this way. And as I move the cursor around, as I move that dot around, the unit tangent vector will continue to point in the direction that the dot is moving. And the normal vector is always just going to point right into the middle. So here's the t slider, and you can kind of see unit normal vector always pointing in, tangents pointing the direction you're always going, then it turns, and unit normal vector keeps pointing that direction, right into the curve. And in 3 dimensions, it'll do the same thing. So eventually I'll come back to that with this. All right, let's see. Oh, in fact, I think we can check what we just got. I want to set that at 2. 2. Ugh, so annoying. There we go. 2. Let's see. Negative 0.97, 0.24 for the normal vector. And it turns out if you plugged in what we got into a calculator, this is negative 0.97, and this is 0.243-ish. So we are good there. All right, hope that helps a little bit.